we're going to look at some examples of applying the comparison test. One thing to note when we use the comparison test is there are a few series we typically compare to, and those are the p-series. Remember that p-series, we know that these converge if p is greater than 1, and they diverge when p is less than 1. A times r to the n minus 1 is the other one we'll use a lot. These are the geometric series. And we know that you look at that ratio of consecutive terms, and when the absolute value of that ratio is less than 1, that implies convergence, and otherwise, if the absolute value of r is greater than or equal to 1, we have divergence. So let's look at a couple examples and see this in action. Let's take the series n equals 2 to infinity of 1 over n squared minus 3 to the 1/3 power. You know, there's a little bit subtracted off here, but otherwise this series basically feels like it would be 1 over n squared to the 1/3, which is 1 over n to the 2/3 power. So the first thing I do when I notice that is I think about this. This is a p-series. We know that the p-series of 1 over n to the 2/3 power, if I were to do that sum, that would be divergent because the p-value 2/3 is less than or equal to 1, and we know the power has to be greater than 1 for us to have divergence. So we're expecting to compare this to a series that is divergent. Therefore, my goal is to find a series that's less than it. So since we think this is like a divergent series, I need to bound it below by a divergent series. Recall with the comparison test, if I want to prove divergence, I need for the divergent one to be the smaller terms. So let's see if we get lucky and everything works out right. Okay, n to the 2/3. If I compare that to n squared minus 3 to the 1/3, just off the bat, that might be hard. But if we step back a step, n squared is going to be bigger than n squared minus 3, so n squared is always bigger than n squared minus 3. Well then, since the cube root function itself is increasing, n squared to the 1/3 power will be greater than n squared minus 3 to the 1/3 power. Now you may be saying, wait, aren't we in the wrong direction of bounds? Except recall that we are looking actually at a series that's the reciprocals of each of these. When you take reciprocals, the direction of inequalities reverses, and the basic reason is we know the thing with the larger denominator corresponds to the smaller fraction if the numerators are the same. So notice I have bounded my series, so this is mine. This is the one that we're seeking out information on, and I have bounded every term of that series from below by the general term of a series that I know happens to be divergent. So from here I'm going to say, since the series of 1 over n to the 2/3 is divergent, and I'm just going to put in parentheses the reason why. It's a p-series with 2/3, which is less than or equal to 1. By the comparison test, our series, sum n equals 2 to infinity of 1 over n squared minus 3 to the 1/3, also diverges. Okay, let's look at another one. Consider the series n equals 1 to infinity of 1 over the square root of n times 3 to the n. Okay, this one's a little confusing to me right now. I'm not naturally sure which it is, you know? Is this convergent because the series 1 over 3 to the n, that's a geometric series, and it's convergent. So since it's a geometric series and it's convergent, and the reason it's convergent is because my ratio here would be 1/3, and the absolute value of 1/3 happens to be less than 1. But I also see within this series that I'm looking at the series for 1 over root n, and that happens to be divergent because it's a p-series with p equals 1/2, which is less than or equal to 1. So right now, I don't have a good feel. Is this series going to converge or diverge? So what I'm going to do is I'm just going to see how would I be able to bound it to figure out which it is. So again, since this is a series where everything interesting happens in the denominator, I'm going to find an upper and lower bound for the denominator, and I'm going to use that to help me make sense of what happens for the original fraction, the reciprocal. So I'm going to take the square root of n times 3 to the n. Okay, well what I notice is that that is certainly bigger than or equal to 3 to the n by itself when n is greater than or equal to 1. Okay, I think I'm going to be okay. I think I can prove it's convergent because the next thing that's going to happen is I'm going to flip this. I'm going to say the reciprocal, 1 over root n times 3 to the n, which is the term we're adding at each step in the series we care about, would therefore be less than or equal to 1 over 3 to the n. Now look at that, and I think back to the comparison test. The comparison test says that if the bigger series, the one we know something about, so we know that sum of 1 over 3 to the n converges. So I have upper bounded every term of my series with the terms of a series that will converge. So I've said I could sum up something even a little bit bigger at each time and I'd get a finite number. Well, the only thing smaller than a finite number is finite itself. So, since I was able to upper bound this with something convergent, this implies by the comparison test that the smaller series is also convergent. Now, you may be asking yourself a question. Well, couldn't I have just said that 1 over root n times 3 to the n is less than or equal to 1 over root n? And wouldn't that have troubled this result? And the answer is no, it wouldn't. And I want to show you why. While it is the case that additionally the general term of the series I had, what I was summing at each step, is less than or equal to just the term 1 over square root n, all I'm saying here is that there's a series whose terms are bigger that diverges. Well, there are a million series whose terms are bigger than anything that happen to be divergent. I mean, I could have just taken the series, I could have bounded this thing from above by 400. The sum of 400, if you keep adding 400 infinitely many times, that is certainly divergent. The thing that determines convergence or divergence of a series is the boundedness of its partial sums. And what we notice here, I haven't done anything that really states that the partial sums of my series might not have a bound if I shows there happens to be something bigger that is infinite. I can only use infinity as a helpful result, something that's divergent as a helpful result if I show it's the smaller of two quantities. Because then if you have two things and you know the smaller one sums up to infinity, then the bigger one will also have to sum up to infinity because there's nothing bigger than infinity. While it is the case that we've established that 1 over root n times 3 to the n is less than or equal to 1 over root n, with the sum of 1 over root n being divergent, this does not violate the comparison test, since divergent has to be less than or equal to the series we care about to imply that the series a sub n is divergent, and we don't have that order, we have it on the wrong side. So a sub n less than or equal to something that diverges tells you nothing.